Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, in this video, we shall study almost all the rules and techniques of differentiation, which are required for any student studying mathematics, science, or engineering. These are the contents of this lecture. Let us start from the first one. The power rule is an important rule of differentiation. This rule says that if we are given x power n and we want to differentiate it, then the differentiation of x power n will be equal to n x power n minus 1. We can see to differentiate x power n, we bring n to the beginning, and then we subtract 1 from the n which is in the power. Let us explain it by an example. We have a function x power 4, and let us differentiate it by using the power rule. According to that rule, we shall bring the power which is 4 to the beginning, and then we shall subtract 1 from the power. So we get 4x power 4 minus 1. And now just simplify this and we can get the solution. 4x power 3 is the solution. Let us find the differentiation of x power 3 by 2. Now again, to use the power rule, we shall bring the power 3 by 2 to the beginning, and then we shall subtract 1 from the power. So the solution is 3 by 2 x power 3 by 2 minus 1. And now taking the LCM, and after simplifying, we get 3 by 2 x power 3 by 2 minus 1 is equal to 1 over 2, and that is the solution. Derivative of a constant, let us say c is any constant, then we shall remember that the derivative of a constant is 0 because there will be no changes in constant. Let us explain it by an example. We have a constant, let us say 3. Now let us differentiate 3. So differentiation of 3 is 0. Let us take another constant, 3 by 7, and let us differentiate this. Then differentiation of this is 0. So differentiation of any constant is equal to 0. Constant multiple. If a constant c is multiplied with a function, then differentiation of c f of x is equal to c differentiation of f of x. From this we can see to differentiate the constant multiple of a function, we shall take constant c outside of the differentiation without differentiating it, and we shall differentiate only the function f of x. Let us explain it by some examples. We have a function x power 4, and there is a constant multiple, let us say 3. Now to differentiate 3x power 4, we can write it as taking 3 outside of the differentiation and differentiating only x power 4. So we get 3. Now to differentiate x power 4 by the power rule, we can write 4x power 4 minus 1. So the solution is 4 3s are is 12 x power 3, and that is the solution. Sum or difference rule. If we are given two functions and they are in summation, then the differentiation of this is equal to the sum of their individual differentiations. Similarly, if there is a minus between two functions and we need to differentiate them, then the differentiation is equal to the difference of the differentiation of these two functions. Let us explain it by some examples. So let us say x power 4 is a function plus x power 3 is another function, and we need to differentiate it. So the differentiation will be equal to d by dx of x power 4 plus d by dx of x power 3. So from this, by using the power rule, we get 4x3 plus 3x squared. Let us write another example in which we have a function x power 5 minus x power 3, and let us differentiate it. Then this is equal to d by dx of x power 5 minus d by dx of x power 3. By using the power rule, this is equal to 5, x power 5 minus 1, which is 4, 3x power 3 minus 1, which is 2. And that is the solution. Let us write another example in this portion, d by dx of 1 over 3 into x3. To differentiate this, we take 1 over 3 outside, and we are differentiating only x power 3. And from this we have 1 over 3, and now by the power rule 3x squared. 3 will cancel with 3 and we get the solution, which is x squared. We use the product rule when two functions are given in product. Then we call one function as first function, the other as second function. Let us say f is first function and g is second function. Then the differentiation is equal to first function differentiation of the second function plus second function differentiation of the first function. Let us explain it by some example. We are given a function x cube into x plus 1, and let us differentiate the product of these two functions. We call x cube as first function and x plus 1 as second function. Then according to the product rule, we shall write the first function as it is, and we shall differentiate the second function, which is x plus 1. Then plus, let us write the second function as it is and differentiate the first function x cube. Now the remaining is just simplification, x cube, and we know that differentiation of x is 1 and differentiation of 1 is 0. Plus, let us write x plus 1. Now differentiation of x cube is 3x squared. Let us simplify this a little more. So we have x cube plus, from here we have 3x cube plus 3x squared. So the solution is 4x cube plus 3x squared. That's all. That's the solution. We use the quotient rule when two functions are given in fraction. The differentiation of f by g is given by g square. Then we have to write g as it is and differentiate f minus f and differentiate g. Let us explain it by an example. In this example, we have to differentiate x square divided by x cube plus 1. Now here f is x square and g is x cube plus 1. So according to the quotient rule, we shall square the function which is in the denominator, x cube plus 1. That is the function in the denominator. So let us take it square. And now write that function as it is and differentiate the function which is in the numerator, x square, minus write x square and now differentiate the function which is in the denominator. And now let us just simplify this to get the solution. So we have x cube plus 1, differentiation of x square is 2x minus x square, and differentiation of x cube, that is 3x square, differentiation of constant 1, 0, whole divided by x cube plus 1 whole square. Let us simplify it a little more. So we have 2x power 4 plus 2x, and from here we get minus 3x power 4 and whole divided by x cube plus 1 whole square. And from this we get 2x cube and the other is minus 3x power 4. So we write 2x minus x power 4 whole divided by x cube plus 1 whole square. And that's all. That is the solution of this question. The chain rule is used when we are given a composite function, just like f of g of x. The differentiation of f of g of x is equal to f dash of g of x into g dash of x. Here we can see that f is the outer function and g of x is the inner function. So to differentiate it, first of all, we shall differentiate only the outer function. And then we have to differentiate the inner function. Let us explain it by an example. Let us write d by dx of x square plus 1 whole power 5. Now to differentiate this function, first of all, we have to differentiate the outer function. So the outer function is, to differentiate it, we will bring 5 in the beginning, then x square plus 1 whole raised to power 5 minus 1 into differentiation of the inner function, which is x square plus 1. Let us just simplify to get the solution. So we have x plus 1 power 4 and the differentiation of x square is 2x plus differentiation of constant is 0. Let us simplify a little more. 2x will multiply here. 5 2s are 10 x into x square plus 1 whole raised to the power 4, and that is the solution. Differentiation of logarithmic functions. There are two types of logarithmic functions. One is called natural logarithmic function, which is denoted by log x to the base e, where e is a fixed constant. Its value is 2.718. It is also denoted by ln x. The other is common logarithmic function. It is denoted by log x to the base a. Here a is any non-zero real number. Let us see how to differentiate the natural log. So the differentiation of natural log is equal to 1 over x. Now instead of x, if there is some function of x, then the differentiation will be 1 over f, and then the inner differentiation of the function f of x. Let us explain it by an example. We have ln x cube plus 1. Let us differentiate it. So according to the above formula, its differentiation is 1 over f of x. Here f of x is x cube plus 1, and then the inner differentiation d by dx of x cube plus 1. So after simplifying this, we can see the differentiation of x cube is 3x square and differentiation of constant is 0. So we have the solution 3x square divided by x cube plus 1. Now the differentiation of common logarithm log x to the base a is equal to 1 over x into natural log of a. Now instead of x, if there is some function of x, then the differentiation of common log f of x to the base a is equal to 1 over f of x into natural log of a into differentiation of the function f of x. Let us explain it by an example. D by dx of log x cube plus 1 to the base 2. This is equal to, according to that formula, we have to write 1 over f of x. Now f of x is x cube plus 1 into natural log of a, and a is here 2, and then d by dx of the inner function, which is x cube plus 1. Let us simplify this. So we have 1 over x cube plus 1 into natural log of 2, and differentiation of x cube is 3x square, differentiation of constant is 0. So we have 3x square divided by x cube plus 1 into natural log of 2, and that is the solution. Differentiation of exponential functions. There are two types of exponential functions. One is called natural exponential function, denoted by e power x. Here e is a fixed constant 2.718, and the other is called common exponential function, which is given by a power x. A is any non-zero real number. Let us see the differentiation of natural logarithmic function e power x. So the differentiation of e power x is the same e power x. But now instead of x, if there is a function f of x, then differentiation of e power f of x is equal to e power f of x into differentiation of that function f of x. Let us explain it by an example. We have e power x4 plus 3, and now let us differentiate this. By using the above formula, we shall write e power x4 plus 3 as it is, and then let us find the inner differentiation of x4 plus 3. So from this we have e power x4 plus 3 into 4x cube plus 0. If we write it in a simplified form. We write 4x cube into e power x4 plus 3, and that is the solution. Now let us see the differentiation of common exponential function a power x. So its differentiation is a power x into natural log of a. Now instead of x, if we have f of x, we shall differentiate it as a power f of x into natural log of a, and then differentiation of this function f of x. Let us explain it by an example. So we have 4 power x square plus x plus 1. Let us differentiate this function. So the differentiation of this according to the above formula is 4 power x square plus x plus 1 as it is, and then natural log of a, so a is 4 here, and then differentiation of f of x, which is x square plus x plus 1. So from this we get 4 power x square plus x plus 1 into natural log of 4, and the inner differentiation is 2x plus 1 and plus 0. So that is the solution. That's all. Let us write a simple example. I have 5 power x square. Let us differentiate 5 power x square. So according to the above formula, I will write it as it is. 5 power x square, then natural log of 5, and then let us differentiate the function, which is x square. So from this we get 5 power x square into ln 5, and the inner differentiation is 2x. So that is the required solution. Differentiation of trigonometric functions. There are 6 trigonometric functions: sine x, cos x, tangent x and their inverse, cotangent x, secant x and cosecant x. The students are advised to memorize these formulas. Differentiation of sine x is cos x. Differentiation of cos x is minus sine x. Differentiation of tangent x is secant square x. Differentiation of cotangent x is minus cosecant square x. Differentiation of secant x is secant x into tangent x. Differentiation of cosecant x is equal to minus cosecant x into cotangent x. Let us use these formulas to solve some examples. The first example is, let us differentiate secant cube x. Now this can also be written as d by dx of secant x whole cube. So first we need to use the chain rule. According to this rule, 3 will come to the beginning, and then secant x power 3 minus 1, and then we need to do the inner differentiation of secant x. From this we get 3 secant square x, and you can see from formula number 5, the differentiation of secant x is secant x into tangent x, and if we simplify it, we get 3 secant cube x into tangent x, and that is the solution. Let us solve another example. in which we find differentiation of sine x into tangent x. Here we shall use the product rule. According to that rule, we write first function differentiation of the second function, then plus second function differentiation of the first function. And now let us use those formulas to find the solution. So we have sine x and differentiation of tangent x. We can see it from formula number 3, which is secant square x. So we write secant square x plus tangent x and differentiation of sine x, which we can see from the first formula, that is cos x. So that is the solution. However, we can simplify it a little more. This is sine x, secant is the inverse of cos, so we can write it 1 over cos square x. Then plus, from tangent we can write sine x divided by cos x into cos x. This cos will cancel with this cos. And now if we take sine x as common, we have 1 over cos square x plus 1. And that is the required solution. Differentiation of hyperbolic functions. Just like the trigonometric functions, there are 6 hyperbolic functions. Sine hyperbolic x, cos hyperbolic x, tangent hyperbolic x, cotangent hyperbolic x, cosecant hyperbolic x, and cosecant hyperbolic x. Their derivatives are same, just like the trigonometric function. The difference is that with all the original function, just like sine, cos, tangent, there is no negative sign. There is positive sign. But with each of the inverse function, just like cotangent, secant, and cosecant, with their derivative, there is a negative sign. Let us use these formulas to solve some examples. In example number 1, let us differentiate sine hyperbolic 5x. This can be written as d by dx of sine hyperbolic x whole raised to the power 5. So first of all, here we shall use the chain rule. According to that rule, we write 5 sine hyperbolic x raised to the power 5 minus 1, and then we do the inner differentiation of sine hyperbolic x. From this we get 5 sine hyperbolic x whole raised to the power 4, which can be written as sine hyperbolic power 4x. And from formula number 1, we can see that differentiation of sine is cos hyperbolic x, and that is the solution. Let us solve another example in which we differentiate cos hyperbolic x into cotangent hyperbolic x. Here we use the product rule because there are 2 functions and they are in product. So we write first function, differentiation of the second function, then plus second function, differentiation of the first function. And from this we get cos hyperbolic x, and differentiation of cotangent hyperbolic x, we can see this is minus cosecant hyperbolic square. So we write minus cosecant hyperbolic square x, then plus cotangent hyperbolic x, and differentiation of cos hyperbolic x, we can see it from formula number 2, which is sine hyperbolic x. Let us simplify it a little more. So we write minus cos hyperbolic x divided by cosecant is equal to 1 over sine. So we write 1 over sine hyperbolic square x plus cotangent is equal to cos hyperbolic x divided by sine hyperbolic x into sine hyperbolic x. Now sine will cancel with sine, and from this we can see, just taking cos hyperbolic x as common, we get cos hyperbolic x into minus 1 over sine hyperbolic square x plus 1, but we write 1 first, minus 1 over sine hyperbolic square x, and that is the solution. Differentiation of inverse trigonometric functions. The differentiation of sine inverse x is equal to 1 over under the root 1 minus x square. Then the differentiation of cos inverse x is same, but we can see there is only a minus sign. Differentiation of tangent inverse x is 1 over 1 plus x square. But the differentiation of cotangent inverse x is same, just like the tangent inverse, but there is a minus sign. Similarly, the differentiation of secant inverse x is 1 over x under the root x square minus 1. But the differentiation of cosecant inverse x is same, just like the secant inverse x, but there is a minus sign. Let us solve an example to use these formulas. D by dx of x square sine inverse 3x. To differentiate this, we can see there are two functions and they are in product, so we use the product rule. First function, differentiation of the second, then plus second function sine inverse 3x, differentiation of the first function. And now from here we can find x square, and let us use formula number 1 to find differentiation of sine inverse x. But here we can see there is sine inverse 3x, so its differentiation is 1 over under the root 1 minus, instead of x there is 3x, so I will write 3x square, and by the chain rule we need to do the inner differentiation of 3x. Now plus second function, which is sine inverse 3x, and differentiation of x square is 2x. Let us simplify it a little more. So we have x square divided by 1 minus 3 3s are 9, 9x square under the root, and differentiation of 3x. 3 will go outside, differentiation of x is 1. So we get only 3 here, plus sine inverse 3x into 2x. So this can be written in this form, that 3x square divided by 1 minus 9x square under the root plus 2x into sine inverse 3x, and that is the required solution. Logarithmic differentiation. If we are given a variable whose power is also a variable, then how to differentiate that? In other words, if we are given a question in which the base is a function of x and its exponent is also a function of x, then how to differentiate it? We shall explain such type of differentiation by solving some examples. So let us start from the first example in which we take x power x. We can see the base is x and its power is also x. Then what will be its differentiation? To differentiate such type of functions, the first step is to put it equal to y. And then we need to take natural log on both sides. So we have to write ln y is equal to ln x power x. And now use the rules of logarithm to write x ln x, because we know that log m power n is equal to n log m. And now we can differentiate both sides. So we have d by dx of x ln x. On the left hand side, we know that differentiation of log y is 1 over y, and then the inner differentiation with respect to x of y. On the right hand side, there are two functions and they are in product. So we use the product rule. First function, differentiation of the second function, plus second function, differentiation of the first function. And from this now we can obtain 1 over y dy over dx, which is equal to x, and differentiation of log x with respect to x is 1 over x. Then plus ln x, differentiation of x with respect to x is 1. This x will cancel with this one. And let us take y to the right hand side. So we have y into 1 plus ln x. And now let us re-put the value of y from 1. So we have d by dx of x power x is equal to x power x into 1 plus log x. And that is the required solution. So to solve such type of functions, just remember that the first step is to put it equal to y. In the next step, take natural log on both sides and use the rules of logarithm to simplify this. Then just differentiate both sides, and after simplification, we can get the solution. Let us solve another question. In this question, we are given x plus 1 whose power is x cube. Then what will be the differentiation of this function? You can see base is a function of x and power is also a function of x. So such type of questions, to solve them, the first step is to put it equal to y. And in the next step, we take natural log on both sides. So we have this thing. Now just use the rules of logarithm. So we have x cube ln x plus 1. And then in the next step, we take differentiation on both sides. So we have d by dx of log y, which is equal to d by dx of x cube log of x plus 1. From the left hand side, we can obtain 1 over y into dy by dx. From the right hand side, we use the product rule. So we write first function differentiation of the second function, which is log x plus 1. Then plus second function log x plus 1 and differentiation of the first function, which is x cube. So from this we have 1 over y dy by dx, which is equal to x cube, and differentiation of log x plus 1 is 1 over x plus 1, and then the inner differentiation of x plus 1 plus log of x plus 1 and differentiation of x cube, that is 3x square. So let us simplify it. We get 1 over y dy by dx is equal to x cube divided by x plus 1, because differentiation of x is 1 and differentiation of constant 1 is 0. And from here we get plus, let us write 3x square in the beginning, log of x plus 1. Now let us take y to right hand side. So we have dy by dx is equal to y into x cube divided by x plus 1 plus 3x square log of x plus 1. In the last step, let us re-put the value of y, let us say from 2. So we have d by dx of x plus 1 whole power x cube equal to x plus 1 whole power x cube into x cube divided by x plus 1 plus 3x square log of x plus 1, and that is the required solution. Differentiation of parametric curves. Sometime we are given y as a function of some other variable, which may be t, theta, u, etc. Similarly, x will be given as a function of another variable, and we need to find the value of dy by dx. Then we shall use this formula to find the value of dy by dx, which is equal to dy over dt into dt over dx. If we cancel dt with dt, we can see both sides are equal. This formula or this rule is called chain rule for parametric curves. Let us solve some example to explain the method. In this example, we are given that y of t is equal to t cube minus 3t and x of t is equal to t square minus t. And we need to find dy by dx. So the first step is that to write the chain rule for parametric curves. Dy by dx is equal to dy by dt into dt by dx. Let us say this is my equation number 3. Now for this formula we need the value of dy by dt. So from 1 we can obtain by differentiating both sides with respect to t. This is equal to d over dt into t cube minus 3t. And now if we differentiate t cube with respect to t, we get 3t square. And if we differentiate minus 3t, minus 3 will go outside, and differentiation of t is 3. So we have 3 into t square minus 1. And now let us differentiate x with respect to t. So from 2 we have just differentiating both sides with respect to t. We have t square minus t, and from this we get 2t minus 1. But in formula number 3, we have to find dt over dx. So let us take the reciprocal of this. So from this we get dt over dx is equal to 1 over 2t minus 1. Let us substitute these values in formula number 3. So we have dy by dx is equal to, let us put the value of dy by dt, which is given here. So its value is 3 into t square minus 1. Now into, let us put the value of dt by dx, which is this one. So we have 1 over 2t minus 1. If we simplify, we can write 3t square minus 1 divided by 2t minus 1. And that is the required solution. In this example, we can see that y is a function of theta, x is also a function of theta, and we need to find the value of dy by dx. So in a similar way, we shall write the chain rule for parametric curves in terms of theta, which is equal to dy over d theta into d theta over dx. Let us say this is 3. Now from 1 we have to find the value of dy over d theta. So let us differentiate both sides with respect to theta. So we have sine theta minus theta cos theta. From this we can obtain the d by d theta of sine theta minus d by d theta of theta into cos theta. Differentiation of sine theta is cos theta. Minus is as it is. Now here we use the product rule. So we write first function differentiation of cos theta, that is minus sine theta. Now plus we write second function, and differentiation of theta with respect to theta is 1. Let us simplify this. So we have cos theta minus minus will be plus, so we have plus theta sine theta, and plus into minus and minus, so minus cos theta. Minus cos will cancel with plus cos, and we get the value of dy by d theta, which is equal to theta sine theta. Now let us write the value of x of t, which is equal to cos theta plus theta into sine theta. And let us differentiate x with respect to theta. So we have d by d theta of cos theta plus theta into sine theta, and this is equal to d by d theta of cos theta plus d by d theta of theta into sine theta. Differentiation of cos theta is minus sine theta, and here again we use the product rule. So we write first function differentiation of sine is cos plus second function differentiation of theta with respect to theta is 1. Now minus sine theta and plus sine theta will cancel, and we have dx over d theta, which is equal to theta cos theta. And from this we need the value of d theta by dx, which is equal to 1 over theta into cos theta. Now we need to substitute these values in formula number 3. So let us write formula number 3 here, which is dy by dx equal to dy by d theta into d theta by dx. And now let us substitute these values. So the value of dy over d theta is theta into sine theta, and the value of d theta over dx, which is given here, this is 1 over theta into cos theta. Now theta will cancel with theta, and from this we get sine theta over cos theta. So the solution is dy by dx is equal to tangent theta, because sine over cos is equal to tangent, and that is the solution. Differentiation of implicit functions. Sometimes the variable x and y are related with each other in the form of an equation, just like this one. And we need to find the value of dy by dx. In such cases, we shall differentiate each term of this equation. After differentiation, we shall separate dy by dx and keeping it on one side. And we shall transfer all the remaining terms to other side of the equation, and that will be the required solution. Let us solve this example to explain the method. We are differentiating both sides of this equation with respect to x. So we have cos x plus x square y minus y square is equal to d over dx of 4 into x. From this we get d over dx of cos x plus d over dx of x square into y minus d over dx of y square. This is equal to 4 into d over dx of x. And now we know that differentiation of cos x is minus sine x, plus here we use the product rule. So we write first function into differentiation of the second function, plus second function differentiation of the first function, minus, now to differentiate y square with respect to x, we shall do outer differentiation just like using the chain rule. So we write 2y power 2 minus 1, which is 1, and then inner differentiation dy over dx, which is equal to 4, because differentiation of x with respect to x is 1. And now let us simplify it a little more. So we have minus sine x plus x square dy over dx plus y into differentiation of x square is 2x minus 2y dy by dx is equal to 4. Now taking common dy by dx from these two terms, we get from here x square minus 2y, and let us take dy by dx as common from these two terms. Write the remaining terms minus sine x plus 2xy is equal to 4. Now we shall transfer all the remaining terms to the right hand side. So we have this is equal to 4 plus sine x minus 2xy. And now let us divide both sides by x square minus 2y. So we have 4 plus sine x minus 2xy divided by x square minus 2y, and that is the required value of dy by dx, and that is the solution. That's all.